so far because we looked at the reactivity of group 1 and group 2 metals, right? We also looked at the melting point of group 1 and group 2 metals. We looked at the conductivity of group 1 and group 2 metals. So some of this we've covered a little bit already, right, in terms of the properties of metals. Fairly straightforward. Draw and label the metallic bonding model. Describe the metallic bonding model. So those two essentially go hand in hand. And evaluate the extent to which the metallic bonding model can be applied, right? So we're going to look at essentially what that means is what are the limitations to the metallic bonding model? What properties of metals can it not describe? Prior knowledge. So from our first topic area, we know that group 1 metals are highly reactive, right? Because they easily lose that electron. In fact, that's the definition of a metal from a chemical point of view. A metal is a substance which easily forms cations, i.e. easily loses their electrons. Reactivity in group 1 and group 2 metals, we know, increases as we go down because the electrons are further away from the nucleus. They're more easily able to be removed. They require less energy. Metals are conductive. We've seen that before. We've looked at the conductivity of group 1 and group 2. Conductivity decreases as we go down. Right? Larger atom increases the resistance in order for those electrons to flow. And that's the definition of a substance that is able to conduct an electrical charge is a substance that has free moving charged particles. In metals, it's the electrons. In ionic compounds, they're not conductive in the solid state because the ions are fixed. In the liquid, molten, or aqueous solution state, the ions are able to freely move and carry the electrical charge. Melting and boiling points, we know, decrease as we go down, and that tells us something about the strength of the bonding, right? Melting point is the temperature at which substance changes from a solid to a liquid. The stronger the melting point, the stronger the bonds are between them. So nothing new here. So like I mentioned before, metal is defined as an element that loses outer shell electrons to become stable. That's linking back with this idea of the octet rule. Oct means 8. Full valence shell is what we're looking for. When a metal loses electrons, it becomes positively charged. Cat positive, positively charged ion. Metals have low ionization energy. Let's break that down. Ion means charged particle. Ionization is the process by which an atom becomes an ion. Energy, the amount of energy required to strip an electron away from an atom. And low electronegativity. Electronegativity is the ability to attract electrons. So if I've only got 1 or 2 in the case of group 1 and group 2 metals, it's much easier to get rid of that 1 or 2 electrons than it is to gain 6 or 7. So we know that about halogens, group 17, that they have high electronegativity. Right? Fluorine, the most electronegative element on the periodic table, wants that extra electron to complete its octet. And the properties we look at are malleability, ductility, conductivity that we've explored a little bit, and this thing called a crystalline structure. Crystalline and lattice go hand in hand. And what does lattice mean? We looked at that in ionic compounds.
It's like the structure, it's not standard, the 3D.
Here's something about 3D. A word maybe starting with R. Reoccurring or regular arrangement is what crystalline means. Yeah? Reoccurring or a regular structure. So something which is a crystal is something that has a regular structure to it. So here are the properties that we look at. Lustrous, which means what? What does luster mean? It means shiny, right? Malleable and ductile. Malleable means the ability to be hammered into sheets or rolled into sheets. Ductile means the ability to be drawn into a wire. If I take a substance and pull either side with forces in opposing directions, it draws it into a wire. Heat and electrical conductivity. If I take a red hot poker, put it into a fire, I'm going to feel it unless I put a wooden end to it or a plastic end to it that doesn't conduct heat. Same thing with electrical conductivity. Must contain free moving charged particles. Here's our different trends of our melting and boiling point: gold, iron, mercury. Mercury is really interesting in that it bucks the trend, right? Mercury's got a melting point of negative 39 degrees. So it's unlike any other metal in that it's a liquid at room temperature. Only one of two elements on the periodic table to be a liquid, the other being bromine, which is a non-metal. And all our others have high melting and boiling points. Tells us that we've got that strong force of attraction between particles. We're not concerned about the actual units of electrical and thermal conductivity, but we've got a rough idea. We can see that it's relatively conductive. Mercury is not very electrically or thermally conductive, and that makes sense. It's got such a low melting point and how it's so different to other metals there. Density, right? Lots of our metals are really dense, and that was in one of our pracs in our Group 1 and Group 2 metals. Right? You looked at the different densities of metals. Density refers to how closely packed particles are together. So mercury, even though it's a liquid, it's incredibly dense. To the point, if you were able to stand in mercury, you would float. You would float on top by standing on top of mercury. It is that dense. So 13 times more dense than water. There's some examples of some non-metals. Oxygen gas, minus 219 degrees. Carbon or diamond, we're going to look at non-metals and covalent substances later. Right. Extremely high melting point in diamond, whereas oxygen extremely low. So we've got huge variability when we look at covalent substances. Uses of metals, I'm not going to go through each and every one of these, and certainly don't expect you to memorize all the different uses of metals. But what we want to be able to consider is every use of a metal is linked with a property of a metal. So copper being an extremely good conductor, we use that in conductive wires. Steel, which is an alloy of a metal of iron and carbon, we use that in building structures, cargo ships, etc. Titanium is a very light, it's got a much lower density but incredibly strong substances that we use to build aircraft. Wires, right? Particularly things like gold, titanium, they are non-reactive metals. We use the property of ductility to draw them into a wire for bracelets and jewelry. We also like the luster of silver and gold in jewelry as well. And that, again, linking that idea, they're non-reactive, they're valuable, they have this really nice luster to them. They can be polished readily. Electricity, right? And huge diverse range of objects. Door handles, cupboard handles, etc. Linking with that idea of that malleability. School desks right in front of you. Right, notice how the school desks are painted as well. That's not just for them to look good. That helps to minimize the corrosion of the metal so they don't oxidize as readily. I'll show that in a future class as a recap. So let's now look at the metallic bonding model. To draw and describe it, there's two main components to the model. It's a three-dimensional lattice, much like an ionic compound, except slightly different. In that, I want you to imagine a box of oranges and how you might stack oranges. And so we've got these big positive metal cations that are fixed in place, or largely fixed in place. And then surrounding them is electrons. And we call it a sea or a cloud of electrons. And they're those outer shell electrons that are more loosely attached to the metal that become free to move in a larger block of the metal. And that force of attraction between that sea of electrons and the cations is really strong. And it's also an electrostatic force of attraction, like ionic compounds, right? All bonding is electrostatic, right? Which is simply the positive and negative charges, opposing charges attracting one another. In ionics, it's the anion and the cation. In metals, it's the cation and the sea of electrons whizzing around. And there's some examples. Right, so we can see this sort of stacking of the cations and the electrons around floating. So zinc has a 2+ ion, and each of those atoms will donate 2 electrons to the sea. Sodium, being in group 1, has got 1 electron that it's lost that's floating around. So the number of delocalized electrons equates to the number of electrons lost in the original metal. Let's consider about explaining these. Luster, all of the properties link somehow with the electrons. So luster is that with a freshly cut piece of metal, the electrons are whizzing around really quickly. That means that light won't penetrate into the metal and will be easily reflected. Metals become dull, as we saw in particularly those reactive metals, because they oxidize. They form that grey or whitish tinge, and copper goes bluey green. Maybe do 2 more. Malleability. The bond is strong that the lattice ever so slightly changes shape but remains in contact. So it's not like with ionic compounds when you hammer an ionic compound, the like charged particles align and repel. This is more like, I don't know, peas in jelly. You can push it and mold it, and it will slightly change shape as the ions move around in this sea and are held together. Conductive. Heat links with partly with the density, and those particles are really close together, so the energy is transferred through conduction. So in order for a substance to conduct heat, it must have particles present. So we can't have conduction in air because the particles are too far apart. In metals, they're close together, so the heat energy is transferred through the vibrating particles. Metals are electrically conductive because they have those electrons that are free moving that can carry the charge through a substance. And other properties that we don't explore in great detail is they have high melting boiling point, right? So strong forces of attraction, and that they are dense, closely packed particles, means that we've got a greater mass per unit of volume. Hardness, not really going to worry about that, that's extension, but hardness simply means a ability for a substance, a harder substance to scratch a softer substance. Mentioned that briefly in ionic compounds. Strength, right, relates to high resistance for a material to be deformed, and you can read more about that later. I might cover this. Do you want to finish off metallic bonding? Yeah, and we'll recap